Hello, my name is Gustavo Carlon, and this is my presentation for the poster named A Class of Multi-Iteration Stochastic Optimizers Using the Mice Gradient Estimator for the Stochastic Numerics and Statistical Learning Theory and Applications workshop. This is a joint work with my collaborators, Luisa Spaff and Ro Temponi. I will start presenting the problem that we intend to solve, the stochastic optimization problem. Then I will discuss the method that we use to solve it, the stochastic gradient descent method, and our gradient estimator named mice. Then I will show some numerical examples comparing our method with other methods. Well, the problem that we intend to solve here, the stochastic optimization problem, is one of finding psi star, which is the argument that minimizes a function, here denoted as uppercase f, defined as the expectation of another function, here denoted as lowercase f. This class of problems is very relevant for many fields like stochastic optimal control, computational finances, optimal design of experiments, machine learning, among many others. Alternatively, one might cast a problem of minimizing a sum of functions, here n functions, as a stochastic optimization problem. This might be advantageous in the case where n is large, and specifically interesting for people in machine learning, because this is how we cast an empirical risk minimization problem. Now I will discuss the stochastic gradient descent method. For a gradient estimator denoted as upsilon here, and biased gradient estimator, the stochastic gradient descent method is given by the following iterative procedure. First, one samples a random vector from its probability distribution, then computes the gradient estimate upsilon, and takes a step to produce a new iterate psi k plus 1. If one controls the relative statistical error of the gradient estimator upsilon, then SGD is guaranteed to converge even using a constant step size. If one does not control the statistical error of upsilon, then the step size must be decreased to guarantee convergence. Now let's discuss our gradient estimator mice that we use to control the statistical error of the gradient estimates in stochastic optimization. Now, the mice algorithm is a variance reduction gradient estimator for stochastic optimization, and it works by building a hierarchy of iterations in such a way that it can reuse information from the previous iteration. Then it can sample gradient differences between the iterates that are kept in the hierarchy, and uses this hierarchy to control the relative statistical error of the gradient estimators. It can be combined with any first-order stochastic optimization method, namely stochastic gradient descent, ADAM, or accelerated stochastic gradient descent. How does mice work? Well, for mice, we build a hierarchy of indices that we keep here denoted as calligraphical L at iteration k, where we define what iterates we want to keep in the hierarchy. For example, in the case where we keep all of them, we have 0, 1, 2, up to k at the k iteration. Then we compute gradient differences, here denoted as deltas. And we define our mice gradient estimator as the sum of the estimate of the gradient differences summed over all of the iterates that we keep in the hierarchy. Well, to make this a bit more straightforward, here I will denote the case where we keep all of the iterations in the hierarchy. Then note that we have here at the end of equation 6, the gradient estimate at the psi 0. And then for L from 1 to k, we compute gradient differences between L and L minus 1. This way we can say informally bring the information from the bottom of the hierarchy at psi 0 up to the kth iterate. To illustrate this in a bit of a more intuitive way, here I made this plot, this graph where we denote the sample sizes as M00, meaning that this is the sample size at level 0, meaning computed psi 0 here, at the iteration 0. So say we start with xi0, we compute a sample of the gradient and take a step to compute xi1. Now we want to use the information that we have here to control the variance at xi1 to compute the next gradient. That's what we do. We compute with sample size m11, meaning the sample size at level 1 at iteration 1, a difference of the gradient between xi1 and xi0. Moreover, we sample more, possibly we increased sample size from m00 to m01, where this difference are the samples that we compute at xi0 at iteration k equals 1. Using all this information, we can compute the gradient and take a step to get xi2. We repeat the process and sample more, sample the gradient difference between xi2 and xi1, use the information that we had so far to get the gradient estimate at xi2, thus use the stochastic gradient descent to obtain a new iterated xi3. Now, as I mentioned before, we want to control the statistical error of our gradient estimate. To do so, we need to have an estimate of the statistical error. This is what I am presenting here. We are specifically interested in the sum of the variances of the gradient differences component-wise. Now, we want to keep the statistical error of our gradient estimator, here denoted as epsilon, below a constant times factor times the gradient norm. Namely, we want to keep the relative statistical error of the gradient estimator below epsilon. Moreover, we want to do so while sampling the nabla F here, the model that we have, as little as possible. And this is what we are denoted here as calligraphical C. In other words, we want to solve the problem here presented in 12, where we want to minimize the sampling cost while keeping the statistical error below the epsilon squared times the norm squared of the gradient. This problem has a closed solution, and for the minimization of expectation, we present the sample sizes for each level for each iteration as equation 13 here. And for the case where we are minimizing a finite sum, in equation 14, where n is the summons number. If we control the relative statistical error for gradient estimators to be less than epsilon, then for the class of L smooth and mu convex, meaning mu strongly convex problems, then we are able to achieve linear convergence iteration-wise for the stochastic gradient descent with mice estimator, with rate as denoted here in red. Moreover, we might want to control the hierarchy of mice. We might want to choose which iterates to keep in the hierarchy, which iterates to throw away. And for this goal, we have these three hierarchy operators here. The dropping operator, which drops the last iteration out of a hierarchy. The clipping operator, which clips the hierarchy at some specific iterate. And the restart operator that restarts the hierarchy at the current iterate from scratch. So to illustrate this, say we have the situation where we have this hierarchy as represented here, where we had started at xi0, took a step at xi1, and now we want to take the step from xi2 to xi3. It might be the case where it is advantageous to drop xi1 out of the hierarchy. Say that, for example, xi2, the gradient at xi2 is better correlated with xi0 directly than if we go through xi1. Then in this case, if that is indeed the case, we check it and we drop xi1 out of the hierarchy and compute gradient differences directly from xi2 to xi0, while continuing to use the information that we computed before at iteration 1. We're not throwing information out except from xi1. Now, the other operator that I mentioned, the clipping operator, would be a case where, say, I have a hierarchy and I decided that some iterate in this hierarchy, it's better to clip it, edit, and throw everything before it out. To illustrate here, say we want to clip the hierarchy at xi1 and discard any information that we had before, say at xi0. And this is what we do. So now xi1 is the bottom of our hierarchy, and we are bringing the information from xi1 until xi3. And the last case is one where it is advantageous to just restart the hierarchy and discard any information that we have so far. And this is what we do here. We forget xi0, and now we are starting from scratch from xi1 to compute xi2. Now let's take a look at the finite sum case where we train a logistic regression model with L2 regularization. And I will present the result for a data set with 11 million points, where we have 28 features, meaning that we have 28 design variables here for our optimization problem. Now I will present you some results for the optimality gap versus number of gradients versus number of iterations and versus runtime in seconds for SGD mice, and compare it with other methods for this class of problem for finite sum minimization, namely SAGA, SARA, and SVRG. What we observe is this, for this case, SGD mice behaved much better than its competitors both in terms of number of gradients, convergence versus number of gradients versus iterations at needing a much smaller number of iterations, and most remarkably in terms of runtime, where the time that it took to run is very comparable to its competitors, meaning that the overhead that we have for computing variances of mice does not dominate the overall cost of the optimization procedure. So in conclusion, here we presented a class of stochastic optimization methods using mice as a gradient estimator, where the main advantages of mice are that it reuses the information from the previous iterations, it adaptively samples from the hierarchy in order to control the statistical error of the gradient. It can be used for both minimization of expectations and finite sum, being more advantageous as the number of summands increased, say in the case of big data. And that for the strongly convex setting, SGD mice can achieve iteration-wise linear convergence. If you are interested in our work, I will recommend that you look at our preprint here, still under revision, named multi-iteration stochastic optimizers. Thank you for your attention.